Now we've talked about the general ways we might construct Taylor series for functions based off of their relationship to other functions for which we already know the Taylor series. Let's go through some examples. So as I noted before, importantly, because the Taylor series we know are those that are centered at 0, this technique is only going to apply when we're specifically asked for new Taylor series that are yet again centered at 0. So to start with, I want to find the Taylor series centered at 0 for sine of x squared. Again, recall that you have the list of Taylor series to know from a recent worksheet that includes these 6 Taylor series here. And in particular, on that list is the sine of x. So that's what stands out to me here. I can see that I can use function composition where my g of x function that's plugged into sine of x is x squared. So to find this, I start by remembering that sine of x has Taylor series sum from k equals 0 to infinity, negative 1 to the k, x to the 2k plus 1, divided by 2k plus 1 factorial. Then I can use function composition to say that sine of x squared must have Taylor series sum from k equals 0 to infinity, negative 1 to the k, and then I replace x with x squared in my sum from above. Importantly, when we're going through these, you want to simplify this as much as possible, and this will become very important when we have to do more than just say function composition if I have several different operations I have to look at in a row. So what I mean by that is I can actually simplify this part to better specify what the power on x is. So yet again, I have the sum from k equals 0 to infinity. I have my negative 1 to the k and my 2k plus 1 factorial. X squared raised to the 2k plus 1 power is the same thing as x to the 4k plus 2. So this here would be my desired Taylor series. And notice that, of course, one way I could find that is using the definition of Taylor series, but that would require me to take several derivatives until I notice a pattern of the function sine of x squared. And because of the chain rule in the first step, very soon you're going to have the product rule involved, and that will get very complicated. So there's something nice about the simplicity of this process where I can use a Taylor series that I already know. Now let's do a similar thing, but looking at 1 over 1 plus x squared. So there are a couple of ways that we could actually go about finding this. One way is to observe that this is the derivative of arctangent of x. So if I make that connection, again, I can start by recollecting the series representation of arctangent, and that is on our list of those to know. That would be the sum from, let's go back to this, from k equals 0 to infinity of negative 1 to the k, x to the 2k plus 1, divided by 2k plus 1. So if I now want to find the series for 1 over 1 plus x squared, I can observe that that's the derivative of arctangent of x, and then differentiate what we have above. So importantly, notice that I'm differentiating with respect to x. The only place that an x shows up is in here. So we can rewrite the other portions of this exactly as they are. But x to the 2k plus 1 now becomes 2k plus 1 times x raised to the 2k. When I think about this power series, we want to consider a couple of things. The one that we started with up here, if we were to write out the terms of that, it would be x minus x cubed over 3 plus x to the 5th over 5, and so on. So for this one, we're going to note that the first term is not a constant term. So we do not have to change where we start the index value. by comparison, if the first term were, say, 1, then we would have to recognize that the derivative of that term is 0 and reflect that by bumping up our starting index value by 1. Now, again, I can simplify this because I have 2k plus 1 divided by 2k plus 1. And this becomes negative 1 to the k times x to the 2k. This, again, is our desired series. But I'll point out, just to give us another option, another way, is to use function composition. So 1 over 1 plus x squared is 1 over 1 minus negative x squared. So if I keep in mind that let's maybe point to it, that we already have a series for 1 over 1 minus x. That's just x to the k are the terms. Then, in using that with function composition, I can replace the x in my x to the k with negative x squared raised to the k. And I'll point out that that's negative 1 times x squared in parentheses. So that's negative 1 to the k times x squared to the k, or x to the 2k. Of course, that's the same exact series we got above. This is just two different ways we could get there. So sometimes you might notice more than one relationship to one of your known series. So for another example, let's see. Oops. Scroll down to, we can look at trying to find the Taylor series for the antiderivative of the natural log of 1 plus x. So again, to start, notice that natural log of 1 plus x is one of our given series here, the third one on there. And that series starts at 1 and has terms negative 1 to the k plus 1 over k. So once I have that, to find the antiderivative of that sum, I can express that as the sum from k equals 1 to infinity of negative 1 to the k plus 1. And sorry, I dropped my x to the k in my series representation up here. So again, I'll point out what I can start with is writing the things that are constant with respect to x. Now I take the antiderivative of x to the k, giving me x to the k plus 1, and bringing a factor of k plus 1 down in the denominator as well. And then what I can finally do is yet again recognize that c here needs to be added on because I'm looking at the indefinite integral of a function.